Okay, welcome everyone. My name is Alexandra Sarafoglou, and the topic I'm going to present today is about the difference between confirmatory versus exploratory analysis, and also what this means specifically for you as students, how you can incorporate this in your thesis projects or for your internship projects. So just a quick introduction, who am I? I'm a PhD student at the Psychological Methods Department at the University of Amsterdam. And my research really focuses on two different topics. The first topic is more technical. It's about the development of Bayesian methods. And my second topic is very much focused on open science and open science related questions. And specifically, I'm doing research on the topic of pre-registration, so what impact it has on the researchers and how we can improve pre-registration, and also on analysis blinding. Other than that, I'm also teaching the research master. I'm not sure if, am I back again? I'm sorry. I think I was gone.
Yeah.
Okay. So yeah, I'm also teaching the research master course, Good Research Practices. And lastly, I'm also one of the founders of the Open Science Community Amsterdam, together with Susanne Hoogeveen. And this open science community, it encompasses the UvA, but also the VU and the HVA. And the SIOS initiative is also part of this open science community. Okay, then a little disclaimer about the talk. So a lot of the slides, especially in the beginning, are inspired by one of the talks that my supervisor, EJ, gave at the TEAP conference in 2016. And I also included the YouTube link in case you want to watch that. It gives a really nice introduction about what open science is. Also, the difference between confirmatory and exploratory analysis and current initiatives on this topic. Okay, so this is the outline of my talk. I'm going to first introduce to you the empirical cycle and what it is and what it means for our research. Then we're going to dive more into the difference between confirmatory and exploratory analysis. And then, as I said before, it's going to be a little bit more practical, and we're going to talk about pre-registration and thesis and internship projects, and also common problems that I saw that students are having when they try to write their first pre-registration. Okay, so let's start. There is a thing, it's called using the data twice. And this is a bad thing. And basically, as early as in the mid-50s, but also in the 1930s, researchers pointed out that it's really important to distinguish the phase of research where we generate hypotheses from the phase where we're testing hypotheses. And basically what their conclusion was from de Groot and also Reichenbach was that when your data inspires your hypothesis, you cannot use the same data again to test the hypothesis. So this is basically the whole idea of why we generate hypotheses and test predictions. So how does this look like in practice in a perfect world? This is where the empirical cycle comes in. So usually the way research works is as follows. We start with sort of old knowledge and old data that could be an experiment you conducted before, or it could be for you students probably something like a literature review or reading on someone else's work. That's your old knowledge. Based on that, you speculate and explore the literature a bit, and from that you derive a new hypothesis that is relevant for your own research. Based on this, you deduce your new prediction, and then in order to test the prediction, you design a new experiment. And what you then do is you're testing your prediction on this new data set that you collected based on the experiment you designed. And we do this by means of statistical analysis. And then there's sort of the evaluation happens, where based on the new data that we collected, we see whether the hypothesis holds or not. And then this knowledge that you gained accumulates into our old knowledge database, and then the cycle continues. So really there are two phases of research here that we see. So the first phase is what Reichenbach called the creative context of discovery. So this is your exploratory research where you go through the literature, maybe you play around with data that you collected before and you produce all your hypotheses. And then there's the statistical context of justification, or the confirmatory research, where you have your hypothesis and your prediction and you test it on your data. And the problem really arises when you're not obeying this empirical cycle, but you're doing a shortcut. So basically, instead of going through the whole empirical cycle here, you're using the data that sparks the idea for an hypothesis, and you test your hypothesis on that same data set. Yeah, so this can happen for a multitude of reasons. Usually people don't do it on purpose, but what could happen is that they obey the empirical cycle. They conducted an experiment, they tested their hypothesis, they evaluated, and it was, for instance, not significant. And then they start digging into the data set again and get new ideas for hypotheses, and then they just test it on the same data again. So this is where this fooling yourself happens. And this is not the way we can do research. And this is not something that was pointed out recently, that there is a problem when people are not obeying the empirical cycle was already mentioned by others before. One example of that is Feynman's conjecture. And it's a nice little story, so I would just read it out loud to you. So Feynman is this very important physicist, and he writes, and it's a general principle of psychologists that in these tests they arrange so that the odds that the things that happen by chance is small, in fact less than 1 in 20. So this is our alpha level. And then where he is a certain experimenter, ran to me and said, calculate the probability for me that they should alternate so that I can see if it is less than 1 in 20. So what happened there is that the psychologist ran some kind of experiment on, I think, rats, and then he found some kind of alternating pattern in it, and he wanted to see whether it's significant or not. And I said, it probably is less than 1 in 20, but it doesn't count. He said, why? I said, because it doesn't make sense to calculate after the event. So after you already looked at the data. You see, you found a peculiarity and you selected a peculiar case. If he wants to test this hypothesis, 1 in 20, he cannot do it from the same data that gave him the clue. He must do another experiment all over again and then see if they alternate. He did, and it didn't work. So what this basically means, and what the bottom line here is that if you just look at your data and you search for some kind of patterns in the data and you test this hypothesis, it could be that you're just interpreting noise, because there will always be some kind of pattern in your data. And then you just say that this is some kind of psychological theory, or that the pattern that you see is meaningful, when in fact it's just by chance. And only if you repeat the experiment on new data and test it again, you can see whether there's actually a system behind it or not. Yeah, this is another example of how old the idea is in order to make this distinction between exploratory and confirmatory research. This is as old as 1878 by Peirce. And Peirce wrote these rules about how good research should be done. And the first rule that he stated says that the hypothesis should be distinctly put as a question before making the observations, which are to test its truth. In other words, we must try to see what the results of predictions from the hypothesis will be. And here we can see that he was really ahead of his time, and you can interpret this as a request for confirmatory research, but also an early request for pre-registration even, because it says we have to put our prediction as question before we even collected the data. And here we can see a little bit what the issue is in our field. So we have here basically the Texas sharpshooter all the way to the left. What he does is basically he just takes a gun and he shoots it at this wall of wood. And only afterwards he paints the targets around them. And you can see that if you would perform any statistical test here, you will draw very different conclusions of, you know, what the ability of this person's shooting skills are than if he would have painted the targets before and then shoot at them. So here it doesn't make any sense to do any statistics, because this is just basically interpreting randomness. Really on the other side of this continuum, you really have this confirmatory research, where you say beforehand what you would expect and how you would conduct the experiment. You just conduct it automatically, and then you just observe the results. And the problem in our field is that a lot of researchers are kind of operating in this space in between. So they're not only doing exploratory research, but they're also not doing purely confirmatory research. They're somewhere in between, where they're kind of either massaging the data, so to speak, in order to get a significant result or a result that is more favorable. Or you could even say they're torturing the data until they confess, basically, and confess means they get a significant result. So what is the bottom line up till here? Basically, if you use your data twice, then all these statistical tests that you're doing lose their predictive interpretation, because you're not testing any predictions anymore. You're just testing what you already saw. And with it, they also lose their statistical validity. And these exploratory analyses that you're doing, basically they introduce a sort of multiple comparisons problem that I will explain in a minute, which increases the type 1 error rate. So here we can say that statistical tests are only appropriate for purely confirmatory research efforts. So when you think of the continuum, if you are all the way to the right, and only then they are appropriate. And in so-called fishing expeditions, where we fish for significant p-values, our data are used twice. So first to provide the hypothesis and afterwards to test them. And here is a nice illustration of such a fishing expedition for significant p-values. On this axis, we see this massaging the data. So basically manipulating the data to get a better significant results. And this comes from variable selection, including covariates or not, transforming the data using different analysis techniques. This is massaging the data on one hand. And on the other hand is finding your hypothesis in the data. So basically you just collect the data and then you look at some pattern that you found and you build your theory around this one. And if you use kind of both of these techniques, then it is very likely that at some point you will find a significant p-value. Okay, so now we're going to get a little bit into the topic of why this kind of multiple testing or repeatedly using the data is an issue. And as I said before, exploratory analysis introduced this multiple comparisons problem, which increases the type 1 error rate. So the probability that we find a false positive finding. And in psychology, we set our maximum allowable probability to make a type 1 error rate at 5%. This is sort of the standard right now. Which means that the probability of not making a type 1 error rate is 1 minus this alpha. And then we can say like, okay, what is the probability of not making a type 1 error rate in a certain number of tests? Then you just take this to the power of the kind of test that you're doing. And the last equation is the probability of making at least one error. So like one false positive finding in a certain number of tests is then this formula here. So 1 minus alpha to the power of the number of tests. So let's look at that, how it looks like in an example. So let's say we conduct on one data set 3 different tests. Then instead of an alpha error of 0.05%, it already increases to 14% to find some significant finding. And this can go quite quickly. So let's say that you have some kind of binomial experiment. So you have a participant that solves a given number of items. Here I called it just heads and tails, but it could be, you know, like successfully solved or not. And you just want to see whether it's above chance level or not. Okay, then you collected your data, you're conducting, then you find a non-significant p-value in this whole data set. And then you wonder why you didn't find this specific effect, because based on the literature, you think there should be an effect there. And you come to the conclusion that maybe the participant has to solve this problem at above chance level, but however, they kind of always have to refocus during the task. So instead of looking at this entire data set, you only look at every second data point that you find. And then you see like, okay, so this test was also not significant. And then maybe you discuss this problem with your supervisor, and then you come to the conclusion that, of course, you know, it cannot be significant because participants usually need some kind of warming up period. They have to get acquainted to the task, for instance. And then you conduct another test that's still not significant. And then you might also add in your theory that they need your warming up period, but they also get fatigued after a while. Then they're not as that concentrated anymore. And all of a sudden, your p-value is significant. So this can happen kind of subconsciously, because like adding these assumptions to your theory, you know, there should be a warming up period and they get fatigued, you know, it makes conceptual sense. But it is not what you predicted from the beginning. From the beginning, you predicted that based on this whole data set, you should find a pattern and not only on this subset. And basically, the more of these tests that you're doing, the higher the probability to make at least one false positive error, basically just interpreting noise, can increase really rapidly. And there was also this really nice study from Simmons, Nelson, and Simonson. So what they did is they just simulated some data sets that are typically for psychology. And what they did is they simulated different scenarios. For instance, people don't collect one dependent variable, but 2 dependent variables. And then one doesn't work, but the other might work. So here, your alpha level the probability to make an error is not 5% anymore, but already 10%. And then maybe you could add 10 more observations if you think that it was just not significant. You just collect more data. That is, instead of 5, you're at 7.7%. And basically, you can increase your probability to find a significant p-value until over 60%, just by randomly adding more observations. Maybe, you know, like starting to control for gender, even though you didn't predict it, or you put an interaction term in your regression designs. You know, things that are reasonable choices, but that you haven't predicted before can really alternate the conclusions that you draw. And something, basically, if nothing was there in the data, all of a sudden you can make something significant. So what are the solutions to this? So the solutions to this problem is basically to specify your hypothesis and your entire analysis plan before you start collecting your data. And for researchers, this means that they should write a pre-registration. And for students, this is already quite nice because at least from the UFA and from our research master students, I know it's already part of their thesis requirement. You guys have to write a proposal where you already describe your design, but also describe your entire analysis plan in there. And this is basically the equivalent of pre-registration. And this is something that the UFA has, or our psychology department has in place in order to prepare you to write pre-registrations later. Oh, sorry. And the only problem with this is, or what I saw from some students, that they write their analysis plan and their proposal, but the hypothesis and the analysis plan are often too vague. And if you don't really specify how exactly you're going to test each and every single thing, or if you don't really know anything about the scale that you're using or the variables that you will include, then all of these fishing expeditions can happen subconsciously because you just don't know what to do. Whether you should control for gender or not, whether to include the warming up period or not, and then you just decide it on the go, basically. And this is where the problems arise. All right, so as I said before, hypothesis and analysis plan are often ambiguous. And in order to illustrate what I mean, I have this really common many analyst example. So here the research question was, are soccer referees more likely to give red cards to players with a dark skin than to players with a light skin? So this is a kind of straightforward research question, I think. So basically, if a student or just a normal researcher would state this question, and they're going to say like, yeah, I'm going to test this hypothesis in this research question, people would say like, okay, this is a pretty straightforward thing to test. You don't have to be super detailed about it because it's kind of obvious. It's not a really complicated longitudinal design or something like that. But even with this relatively easy example, there are a lot of analytical decisions that you could think about before. For instance, what kind of statistical method are you using? Are you just going to use a normal chi-square test? Are you going to use a logistic regression or some Bayesian version of that maybe? Then also, how is dark and light skin measured? Like, what kind of measurements do you have? Is it only a dichotomous factor? You're either dark or light, or are there multiple levels? Are you going to control for the referee skin color or not? Will you treat each red card decision as an independent observation, or maybe just some referees are racist but others are not? And what about other ethnicities, for instance, Asians? Are you going to put that kind of in your research question or not? So yeah, so these are all kind of decisions that you have to make beforehand. And it can be really complicated. And a lot of researchers, what they do is basically they're not really specific about these things, and only after the data come in. And they basically have to start coding their data file. They have to decide on all of these decisions. And then it's really easy to kind of subconsciously take the route that gives you a favorable result. And this was actually part of a many analyst project, which means that a lot of researchers analyzed the same data with exactly the same research question. And what they found was that the results were very different. So from, I think it was 30 teams, every single team came up with a different statistical model. And depending on kind of the model that they choose, you know, some were like very significant with really kind of big effect sizes. There were also some that found null effects. So it's not always that straightforward as we think. Like a lot of the times researchers, but also students think there's just one way to do statistics, but there's a lot of different ways that we can justify how we code our variables and what kind of analysis pipeline we use, how we pre-process the data. And all of this will have influence on the results that you get. And this is why it's even more important to be like really specific about what you're going to do, because even small tweaks can make basically like a non-significant result into a significant result. And we don't want to avoid significant results, but we want to avoid it if it's, you know, really nothing is happening there. Then another common problem that I see a lot is that some crucial information is missing. And this is more often for the stage of the pre-processing of the data. For instance, where every single time you do kind of survey studies and you include measurement scales, for instance, like some kind of well-being measurement scale with 18 items and specific subscales, researchers often are not really specific about, you know, whether they're gonna use every single item in their analysis, whether they will only include a subscale, whether they take just the mean of all variables and then they only have one dependent variable. So these kinds of things are good to keep in mind every time you're using a scale, to really be specific about how are you going to combine all these items in your survey, for instance. And then also the measurement of the dependent variable. So one example is some research where people wanted to see whether classical music improves attention. So a very common task to measure attention is this kind of Q&O task. So basically people just see a screen like that, and then they have to press a button when they see an O. But here attention can be kind of measured in two different ways. You can look at the reaction times, you know, are people slow or fast in responding, but you can also look at the error rates. How often do people make mistakes? So which of those are you going to use now as attention measure? Like only one of the two or both? It's not enough to only say in your methods part of your proposal that you're going to use this specific test to measure attention, because in the end you might end up with two dependent variables instead of one, and then it's not clear which one you're going to use in the end. And then lastly, what's another thing that's often missing is basically how we determine and exclude outliers. So are you just going to look at your data and basically plot them in a box plot and see where the outliers are? Are you going to use the ±2 standard deviations from the means, or are you going to use some other kind of cutoff? You also have to be specific about that, because depending on whether you're using a box plot or you're using this rule with the 2 standard deviations, in one case you might end up with 8 outliers, and the other you might end up with 28 outliers. And those can be the outliers that make a non-significant finding into a significant one, or vice versa. And the last problem I wanted to address is something that I saw as a student advisor a lot, and also with my own students, that often the statistical models, but also the study designs, are too complicated. So then people come up with a really complicated kind of structural equation modeling where everything kind of relates with everything else. And this is what they put in their proposal. And then after the data come in, they don't really know how to handle it. Like maybe they can implement it in R, but then the model doesn't run. There are like some issues with the chains or something like that. And then all of a sudden they cannot follow through what they actually had planned. So yeah, and the reason for that is that a lot of times people aspire to like develop and test some kind of novel theory, or theory that they came up with themselves. It's often the case that there are too many research questions, and there are too many research questions as well. So what I usually advise is to stick very close to existing literature. So basically not inventing the real new, just add like one small new theoretical assumption that you want to test, and don't come up with a completely new model yourself. and also kind of use the same methods and analyses that you're already familiar with. And just in general, keep it simple. So I rather read like a good internship or a thesis project where, you know, maybe the analyses are not very sophisticated, but therefore I'm very sure that the student understands what is done. It is really good explained, the results are really clear, than kind of a complicated model where it's not really clear whether you understood it or not. And then there's all kinds of issues and problems when you want to code and analyze your data. And one thing also to avoid when talking about, you know, adding covariates and adding random demographics that you collected, if you in your proposal know already that something like age or gender or something is not relevant to your research question, then don't ask your participants their age and gender. You know, it's just this tempting in the end, because you have like this 10 demographics, you just also throw them in your regression model, and then one of them gets significant, then it's really tempting to just keep it in the model, even though you never wanted it in the first place. And yeah, basically what we also see, I mean, also with researchers, that there's a lot of the times just insufficient feedback on, you know, the study design and also the analysis plan. And in psychology, we have this Methodologiewinkel, or the methods shop, that is specifically designed or for students to go there basically even before they collected the data, just to brainstorm about their study design, you know, what kind of variable they should use, what kind of measures they should use, and also about their analysis plan. So students usually go there really in the end of the semester when they have pressure and they have to write up their thesis. But the people who work there are usually very happy if you come in the beginning of the semester, when you still can actually change something, you know, about your study design. Just makes it easier, and it is open for everyone who writes their, I think, internship and thesis projects. And this is a nice little service. Yes, lastly, is that analysis plans have not been tested. This is also a problem that researchers have very often. So you're really detailed in your analysis plan, in your proposal, and then the data come, and then you realize that something doesn't work out, something doesn't converge, or you have forgotten an important step in your analysis that you didn't specify beforehand. And what we're kind of forced to do in our lab is always to create some kind of dummy data, or some data that resemble your experiment. That can be data that you simulate yourself somehow, that can be data from a similar study, for instance, from your supervisor, some kind of survey data if you do survey research, and then you can basically write out your entire R code or SPSS syntax already. And if you then get your real data, you just have to run it again and you're done. So this is really nice and highly recommended, because this is basically the most complete way to a pre-registration, to, you know, write down what you want, but also to actually code it up. And the benefit of it is that you can try out your analysis. You can also try out, you know, do you understand what comes out of it? Can you interpret the results? And with this kind of code or SPSS syntax, you can also ask specific feedback for this analysis. You can give this to your supervisor and say, hey, is this how you imagine it, or should we change anything in the analysis plan? And this also has a drawback, of course, because yeah, we say you have to be really specific and really detailed now. And the problem is a little bit the time pressure of students. So I think this is kind of the plan of a standard research master project or a bachelor thesis project, I'm not sure, 16 weeks. And in the first 8 weeks is basically where we would write the proposal and do all our literature research. And what I basically said now, that here in these first 8 weeks, you also kind of have to create your dummy data, analyze them, adjust the analysis plan, and have one round of feedback in between. So doing it really rigorously might mean that you will come more into time pressure. On the other hand, then the later part of your project where you actually have to analyze the data gets a little bit less stressful because you have your code already in place. And if you kind of approach your supervisor about it, and you might even be able to push the data collection phase to the back a little bit because you want to just write a really nice pre-registration document. And I would say most or if not all of the supervisors at the UFA will be open if you want to say you want to write, you know, a more detailed proposal or a real pre-registration document, and will also give you more time for it. Okay, so yeah, here a little summary. It's important to distinguish the confirmatory and exploratory analysis. Otherwise, you just might end up analyzing noise or randomness in your data, like we saw with this easy example with the successes and failures. And in order to do that, the best way is to decide on an analysis plan before you start collecting your data. And in order to do that, the best way is, you know, to write it all out and to create dummy data or use kind of pilot data from some other study. And if you then write your proposal to be as specific as possible. So in your hypothesis, but also in your analysis plan. And I think the most important tip is just, for me at least, to keep it simple. Like supervisors are always happy to have maybe a little bit of a simpler model or a simpler design, but therefore it is really well executed. This is better than coming up with a really complicated plan and 14 research questions that you're interested in. And finally, it's also okay to make mistakes. Like even with more senior researchers, we write pre-registrations that don't work out in the end because something unexpected happens in the data collection phase. That's all part of the process, and it's fine like that. Then you just add a little paragraph in your thesis where you say deviations from your pre-registration, and then you just say why you changed what in your analysis plan. Okay, then just a little advertisement for open science initiatives at UFA. So basically, if you really want to get into pre-registration and want to learn more about it, where you can go. So first, of course, is the SIOS initiatives. I mean, apart from the talks here, I think you also organize workshops, for instance, about pre-registration. Then in general, the open science community, which is also a bit more targeted towards researchers when you start your PhD or something like that, then that might be more interesting. Then there's a journal club, reproducibility. There's I think one at the UFA that wasn't really active during the pandemic. There's a really active one at the VU that I think you can also attend. Then the Methodologiewinkel that I mentioned before for your internship thesis. And for researchers, we have the Stat Store, where basically researchers and PhD students can go for methodological questions. And that's it. Thank you a lot for your attention.